Okay, I'll talk a little bit about classification of models and optimization problems. So this is going to be a bit lighter. We had the original problem early on where we had a nonlinear objective function, very generic nonlinear constraints with both lower and upper bounds that can be minus infinity or plus infinity, linear constraints, and simple bounds that are just bounds on the variables, and then the condition that x and y is an integer. And to classify optimization problems, we typically look at the class of objective function, the class of constraints, and maybe the structure of constraints and type of variables. Okay, so the easiest problem in many ways is unconstrained optimization problems. So I'm looking now at problems that only have continuous variables. So that's one classification. I'm just looking at continuous variables. And unconstrained optimization is the easiest case. I'm just minimizing a function f over the whole set Rn. It's a continuous problem. A very important special case, our least squares problem, where my objective function is a sum of residuals Rj of x. And they could be scaled, for example, by some variance, parameter sigma or something. This is a very important problem because it arises, for example, in inverse optimization problems or reconstruction problems where you're reconstructing from data, you're reconstructing a sample. Slightly more complex is a bound constraint optimization problem where I only have bounds on the variables. And a special case is the case where f of x is a linear function, and that's solved trivially. So you will get an exercise for that later on. So hold on to that, and you can start doing that exercise now. Next up are linearly constrained optimization problems. So those are optimization problems that have a nonlinear objective, but linear or affine constraints. And then there are two important special cases, linear programming or linear optimization, and quadratic programming or quadratic optimization problems that basically specify that the objective is either linear or quadratic. And without loss of generality, we can assume that the constant term in this quadratic function is 0. And again, we'll have a little exercise at the end for that. So now, another important case are equality constraint optimization problems. And these are special because in some ways it's easier to handle if there's just equality constraints. So ignore that this is a c of x now, it should be a g of x. And the easiest case is probably the case where you have linear equality constraints. This is a nice case because you can, if you're inside the feasible set, you can either factorize the matrix A, or you can easily project into the matrix A, into the null space of A, and then have methods that remain feasible throughout the iterations. And then the most generic problem for continuous optimization variables is the one where we have very general nonlinear optimization problem, some nonlinear constraints with inequality constraints, possibly with equality constraints, some linear constraints, and some simple bounds. And we call this also a nonlinear programming problem. So again, that's sort of the nonlinear programming, nonlinear optimization problem, or nonlinearly constrained optimization problem. I like to emphasize the fact that there are nonlinear constraints because that's actually a harder problem than if there are linear constraints or affine constraints. So that's a nice distinction. The next classification that we can do is by variable type. So we can distinguish continuous variables. We looked at continuous problems for now, and then discrete variables. And so discrete variables arise in many guises, in many different ways. They could be binary variables, in which case they model logic constraints, or general integer variables, like on this integer lattice up here, where the red dots correspond to combinations of integer variables. They could also be discrete variables that are, for instance, pipe diameters. And so Professor Mahajan or Ashutosh will later on, he'll tell you about a problem that rises in the design of a water network where you have, in fact, potentially discrete pipe diameters. And so whenever we have discrete variables, then we get discrete integer optimization or programming problems. And in many cases, we have a mixture of both continuous and integer variables. So we call them mixed integer optimization problems. And this is what we study in this course. So that's sort of critical. There are other classes of variables that are really much harder, and we're not going to look at in this course. And so here's one example where we look at state or control variables. And so those are infinite dimensional variables. X of t is a variable x that now depends on time. So there's a time horizon, and you're applying a control over that time horizon. Or u could be a variable that now depends on t for time. And x, y, z are here spatial coordinates. So this is a 4-dimensional field, u. And this is an example of a topology optimization problem where we're trying to construct an electromagnetic cloak. There's an incident wave going from the bottom to the top. The left picture shows the superposition of that incident wave and the wave that's generated from the cloak that you see on the right-hand side. So this is sort of the optimal cloaking design. These are really hard problems to solve because you have very, very large linear systems and possibly thousands or millions of binary variables. There are random variables, and they arise, for example, in robust or stochastic optimization, when we're, for example, minimizing the expectation. And these problems are hard because they're infinite dimensional optimization problems. So things get a little bit hairy or harder when you work in infinite dimensions. Not all norms are equivalent, for example, and there's issues for convergence that are much, much harder. But we can always revert back to a finite dimensional case by discretizing problems on a mesh. We do that anyway when we solve these problems numerically, or drawing random samples, and we're back at standard nonlinear optimization problems. Another class of variables are semi-definite optimization problems that involve matrix variables. So here now, the variable x is a matrix, a square matrix that's positive semi-definite, meaning all its eigenvalues are non-negative. And the class of problems that we'll talk about tomorrow are second-order cone constraints. And so these have very special structure where you divide the continuous variables up into two sets in this cone. There's a sort of x0, a single one, and then all the other x's. And that's also known as the ice cream cone. And there's a nice generalization that this generalizes non-negativity to these cone constraints, which then allow to give good relaxations, for example, of power grid problems. We're not going to talk about this much, but you can also distinguish by its functional form. So in our case, we're going to assume that our functions are continuously differentiable or twice continuously differentiable. But if they are non-smooth, like in this example up there, where the level sets now have corners, sharp corners, those are also interesting problems. And they arise, for example, in compressed sensing, where you're minimizing an objective function that's a linearly squares form. So you're trying to fit parameters x that fit some basis a to these observations b, but you add a one norm term to it, and the one norm that's basically the absolute value. And that has got kinks, so that's just the absolute value, always has kinks. And so those problems are very interesting. They can be transformed into smooth problems as well. We're not going to talk about multi-objective problems. In many, many applications, you really have more than one objective. So for example, when you're designing aircraft, you might trade off fuel efficiency versus takeoff weight or other such factors. And those are typically modeled, or one way of modeling them is to rewrite these multi-objective problems by summing up these different objectives into a single objective and then minimizing over a convex combination or a linear combination of these objective functions. So I can always transform it by just giving a weight to each of the objectives, and that is basically chosen by the modeler often to say how much emphasis do you place on each objective. So here I have two objectives, F1 and F2, and there's this notion if the problem is convex, there is a Pareto front, those are the green points there, or the green line, and what we're interested in now is maybe choosing different weights to explore this Pareto front and finding different black points on this Pareto front. But that makes the problem much harder because you have to solve an optimization problem each time you want to find one of those points. Okay, and then, so optimization, we can classify by type of constraint, type of variable, or functional form. I really need to start using a spell checker here. It's a broad and rich modeling paradigm, and inequalities are sort of at the heart of optimization in many ways. They make the problem much more interesting, a much richer way of solving problems. And then I have a couple of little exercises if you want to try them. So first of all, an easy optimization problem. I don't know if we have, we have 5 minutes or so. Yeah, we have 5 minutes, okay. Okay, so here are two easy optimization problems. The first one is solve minimizing a linear function, an affine function, over the box. I see people smiling. You've done this before. Okay, you can tell me what the solution is. You should be able to read it off. And then the second one is to show that if I solve an optimization problem where I minimize f of x plus a, then I get the same solution if I didn't have an a in there. And the question, what happens if c of x plus a is less than or equal to 0? Does the same still hold? So get some pieces of paper out, or if you can do this in your head, do it in your head. I don't think I have the solution on here, but we can do it on the board. I'll wipe the board and somebody can tell me what I need to write down. The second one you can also prove by picture if you prefer that. That's perfectly acceptable. I've done lots of proofs by picture. So.
First one is the easy. No, it depends on the sign of C. Depends on the sign of C essentially. C is positive, then Ci is positive, then Li C is negative.
Okay, I see lots of people looking bored. So you already have one of the solutions? Yes. I see people. Okay, how do I solve this first problem? Yes.
If Ci is less than equal to 0, then Xi is in line, and if Ci is greater than 0, Xi is in line.
Okay, so let's do this slower. Oh, okay. So we're going to look at the sign of Ci. We want to minimize this. So if Ci, what did we say, is less than 0, then what do I want to do?
xi is equal to ui.
Xi is ui. Okay, so let's just make sure I understand this. So if Ci is negative, then I want to make this as small as possible, so I'm going to make Xi as large as possible. So I'm going to take ui. Okay. Next one was Ci. Okay.
Then xi is li.
Xi is Li. So if this is positive, then I want to make Xi as small as possible because I'm minimizing this. Okay, what happens if Ci is equal to 0?
It's anywhere.
It can be anywhere. Okay, anywhere in the interval. Yeah, okay. Okay, so you can think of this, you have a box and you have a linear function over it, and you just keep going down to the corner on the box where everything is minimized. That's one way of thinking about this. Okay, I don't think I got a good answer for the second one. So does anybody have a good answer for this one? Yeah.
In first case, there is feasible reason doesn't change.
Sorry?
In first case, I mean, constraints are c of x less than or equal to 0. In both cases.
Yeah, okay. So okay, we take a solute. Okay, so we're going to go x solves, or let's do x star solves. Let's call it the left problem. Then it follows that c of x star is less than or equal to 0.
So in both cases, feasible region is same. I mean, convex hull is same.
Say that again, sorry.
In both cases,
Yeah.
feasible region or convex hull, that is same.
Yeah.
So if we take the contours of f of x or f of x plus a,
Yeah.
so it will be same. I mean, consider f of x to be 0, start increasing it or decreasing it.
Yeah.
So then, if I take f of x to be equal to a, then I'm coming from top, I'm moving downwards towards the optimal solution.
Yeah.
If I add any constant to it, I will be starting from higher value, and
Yeah.
I move towards it.
I think I'm going to draw a picture. So if this is f of x, then f of x plus a would be
Contour.
and so the minimum, the lowest point is independent of A. You can also, if you know first order conditions, the Karish-Kuhn-Tucker conditions, then you can write them down for both problems. And because A is independent of X, the gradient disappears, and so the first order conditions are equivalent. That's a more formal way of proving it, but I haven't told you about first order conditions. And I was going to say we're not going to talk about constraint qualifications. So.
You also use the definition of optimal solution.
Yeah, you could do that too. You use, oh, that's a very good one. You go back to the definition of optimal solution, and then you know that x star is optimal here. That means there's no f of x that's feasible, that's in the neighborhood for which this is greater. But a is always the constant. So you have, I like that. Okay, so we continue our formal proof then. So great collaboration here. So now we do, so we know that it's feasible. And then the definition of a global minimum is that f of x star plus a is less than or equal to f of x plus a for all x such that c of x is less than or equal to 0. Right? But that's equivalent to saying f of x star is less than or equal to f of x for all x such as c of x is less than or equal to 0. So feasibility is, we have equivalence of feasibility because the feasible set is the same, and then we have equivalent of optimality by just looking at the definition. And what happens if I put an A into my constraints? Does that still hold? Who thinks it still holds? Okay, I was hoping to. And who thinks it doesn't hold anymore? Okay, good. You're right, I was wrong. It doesn't hold. So if C of x plus A, if you add an A to the constraints, then it doesn't hold anymore. And the reason is that you're now changing the bounds on the feasible set. So if an example would be if, so I have an example here. If C of x is given as x1 squared plus x2 squared minus r less than or equal to 0, then that's a circle of radius r. And if I now add an a to it, then I have a radius of, I get a different radius circle. So I change the radius of my circle. And that's a different feasible set, and then I can have different minima. So to show that something isn't true, you just need one example. That's a lot easier sometimes. Okay, sorry that these exercises were so easy. But we'll meet back in the afternoon. And you're going to get a different person up at the front, I think, in the afternoon. So, but thank you for being here. Yep, let's give yourself.